Now that we've seen how the Michaelis-Menten equation relates the kinetic constants of Km and Vmax to reaction velocity, let's try to get a better idea of the significance of these constants. Recall from an earlier lesson that when the velocity is at 1/2 Vmax, the substrate concentration represents the value of Km. What does this have to do with what happens inside a living cell? If you think about it another way, it means that if the substrate concentration is much less than this value, less than the Km, the enzyme is not working very efficiently. We find then that the value of Km often gives us a good estimate of substrate concentration in vivo. We've talked about Km as being an equilibrium dissociation constant. Let's see if we can prove that mathematically. Looking at our expression for Km, we see that it is a ratio of the rate constants from our simple reaction scheme. The rate constant K1 is the rate of the formation of ES, K-1 is the rate of ES dissociation, and K2 is the rate of product formation. If the rate of ES dissociation, that is K-1, is much greater than that of product formation, K2, then the value of K2 has little effect on Km, and our expression simplifies to the ratio of K-1 to K1. In other words, it is the rate at which ES dissociates as compared to the rate it forms, a true dissociation constant. Perhaps this will help us better understand that Km is a true measure of substrate affinity. One of our assumptions in this simple model is that there was only one irreversible catalytic step and one rate constant for that step, K2. At levels of saturating substrate, initial velocity, or V0, is equal to the value of Vmax, which is simply K2 times the total concentration of enzyme. The constant K2 is also called the catalytic rate constant, or Kcat. Substituting this into our expression and rearranging it slightly, we see that the Kcat is equal to the value of Vmax divided by enzyme concentration. We call this the turnover number, and it is simply the moles of product formed per mole of enzyme per second. Remember, the Vmax is simply an average maximum speed for all of the molecules in solution. If we divide by the amount of enzyme present, then we're looking at the speed of each enzyme molecule. If we compare Kcat and Km values for some enzymes, we might see quite a difference. Let's compare the enzymes carbonic anhydrase and lysozyme. If we consider Kcat, or turnover number, we see from our table that carbonic anhydrase is orders of magnitude faster than lysozyme. On the other hand, by comparing Km values, we see that lysozyme has an affinity for its substrate 500 times that of carbonic anhydrase for its substrate. Yet these very characteristics are perfectly suited to their respective functions. Recall that carbonic anhydrase converts CO2 to carbonic acid. The concentration of CO2 in our blood and tissues is very high, so it doesn't really need a high binding affinity. It does, however, need to rapidly convert to product in order to maintain blood pH at neutral. Lysozyme is an enzyme that degrades bacterial cell walls. Having a very low Km means that it will find bacterial invaders at very low concentrations. This is a good thing. The speed at which it accomplishes the reaction is not so critical. Hopefully from this you can see the power of knowing the kinetics of an enzyme. They can tell us a lot about what enzymes do, as well as how and why.